Hello, in this video we're going to be finishing off section 8.4 on series and their notation. So just as a brief reminder, series are very similar to sequences, except we are going to be taking the sum of the terms in a sequence as opposed to just creating a list of values. So if I have, for example, an arithmetic sequence like 2, 4, 6, 8, 10, and so on, I can make this into a series by simply adding those terms or finding the sum of the terms in that sequence. We can find what we call partial sums. Say if I want the sum of the first 5 terms, and that would simply be, just as I said, the sum of the first 5 terms in that series. We can find infinite sums, so the sum of the entire series, and that's what we're going to be talking about today, is whether we are able to find a particular value for the sum of an entire series or not. So example 847, on Sunday morning after a minor surgery, a woman is able to walk a half mile. Each Sunday she walks an additional quarter mile. After 8 weeks, what is the total number of miles she has walked? So go ahead and take a minute, pause the video, and try this one out on your own. So our first Sunday she walks 0.5 miles, and then every Sunday after that we are adding on a quarter mile. So then we've got 0.75, then we have 1 mile, 1.25, and so on. If we write this using summation notation, we would start at the first Sunday and end at the 8th Sunday. We are starting at 0.5 miles and adding on 0.25 to every Sunday except for the first one. So finding our sum, we can use our formula, which is 1/2 multiplied by the number of terms times the sum of the first term and the last term in our series. Oops, that should be a sub n. So what I need to do is I need to find a sub n. So I need to figure out how many miles she walked on that 8th week. So a sub 8 is going to be 0.5 plus 0.25 times 8 minus 1, or half a mile plus 0.25 added on for each of the 7 weeks after the first one. So 0.5 plus 1.75 is going to be 2.25. So that 8th week she walked 2.25 miles. So the total is 1/2 times 8 times 0.5 plus 2.25. Half of 8 is 4, and when I add 1/2 and 2.25, I've got 2.75. 4 times 2.75 is 11. So over those 8 weeks, she walked a total of 11 miles. We can also find partial sums for geometric series. So we've got a formula here shown. I've got my formula for a geometric sequence, and then to find the summation, we use sigma notation, starting at the first term, ending at our last term of that geometric series, is going to be found using our formula here. So we can use that formula to find the indicated partial sum of each geometric series. So the first thing I'm going to do is I am going to write this using summation notation. So my a sub n, since this is geometric, is going to follow the form of a geometric sequence. So a1 is 8, and then to get to the next term I am multiplying by negative 1/2 to the power of n minus 1. So then using sigma notation, I'm starting at a k value of 1. And here we have 11 terms. They want us to find s sub 11. So we're going to the 11th term of 8 times negative 1/2 to the power of k minus 1. So the sum of those first 11 terms then, we can use our formula to find. a1 is 8 times 1 minus my r, which is negative 1/2, to the power of n, which is 11, all over 1 minus my r, which is negative 1/2. Simplifying, I have 8 times 1 minus, and negative 1/2 to the 11th power is a negative 1 over 2048, all over, and the denominator I can simplify to 3/2. So that numerator, 8 times 1 plus 2048 is going to give me 2049 over 2048 over 3/2. Reducing my 8 with my 2048, I've got 2049 over 256 over 3/2. And to simplify further, I multiply by the reciprocal of that denominator. So I have 2049 over 256 multiplied by 2/3. I can reduce my 256 to 128. And 2049 divides by 3 to give me 683. So when I reduce, I have 683 over 128. So the sum of those first 11 terms in my series is 683 over 128. So all I did is I used my formula, and then from there I simplified that ugly fraction down as far as I could. Now in B, it looks very similar to what our formula tells us to do directly. However, I want to take a closer look at our exponents. This is a1 times r to the power of k minus 1, while here I've got my a1 times r to the power of k. So I need to do some manipulating to make sure that the forms match. So this 3 times 2 to the power of k, I actually want to be a k minus 1. So what I will do is I will go ahead and divide by 2 and then multiply by 2. And the reason that I do this is because dividing and multiplying are inverses. So if I divide by 2 and multiply by 2, I haven't changed the value of the expression at all. Now I can simplify this component of my series and subtract exponents. So 3 times 2 to the k minus 1 multiplied by 2. And I'll simplify further by multiplying the 3 and the 2 together, since these do not have exponents that I need to worry about. I've got 6 times 2 to the power of k minus 1. So what we're actually looking at in sigma notation is from 1 to 6 of 6 times 2 to the k minus 1. And now that my form matches, I can go ahead and use my formula. So the sum of my first 6 terms is a1, which is 6, multiplied by 1 minus r, which is 2 to the power of n. Here I'm looking at an n value of 6, all over 1 minus r, which is 2. So I've got 6 times 1 minus 64, all over a negative 1. 6 times negative 63, all over a negative 1, which simplifies down to a positive 378. So the value of our sum from the first 6 term of our geometric series is 378. All right, go ahead and take a moment, pause the video, and practice this one on your own. At his new job, this employee is earning a starting salary of $26,750. Each year after that, he receives a 1.6% annual raise, which means we are multiplying by 1.016. We have 100% of his salary plus this 1.6% of his salary to give us this multiplier of 1.016. And then our power is n minus 1. We get that raise of 1.6% every year after the first year, so n minus 1. And we want the total earnings of the first 5 years, so I want the sum of the first 5 terms in this series. So I start at k being 1, and I'm ending at 5, which means that here I should actually have k as my variable instead of n. So using my formula, I have a1, which is 26750, multiplied by 1 minus my r, which is 1.016, to the power of n. Here I'm looking at those first 5 terms, over 1 minus 1.016. And simplifying, I see that his total earnings over those 5 years is $138,099 and about 3 cents. In example 8.4.12, I'd like to look at what happens to our series as we continue on when we are multiplying by values of 1/2. So if n is 2, then 1/2 to the power of n is 1/4, or 0.25. To the power of 4 is 0.0625. To the power of 6, we've got 0.015625. To the power of 10, I've got 0.000977. To the power of 20, I've got 0.00000954, and to the power of 30 is 0.00000000, and so on, 931. So as we are looking at our values, as our exponent increases on this fraction, our values decrease to an infinitely small number that isn't going to make a huge difference to our series. So as we increase our n value, the values that we get for our terms become insignificantly small. That helps us evaluate infinite geometric series. So if we are multiplying by values that cause our terms to decrease into infinitely small numbers, then we can actually add or find a value to which our series converges. Because eventually we're going to be adding numbers that are so small, they're not going to be making a difference to the value of our series, or not going to be making a significant enough difference to the value of our series. Now this only works in cases such as this one, where as we increase our exponent, the values that we are adding are decreasing. If we are multiplying by a value of 2, for example, when I increase the exponent on 2 to the n, I would have 2, 4, 8, 16, 32, and as I'm adding these values, they are actually growing infinitely. So we won't be able to find a particular value to which that series converges. But here in these, if our multiplier is between 0 and 1, then we can find a value to which the series will converge. So all we're going to do is look at the common ratio of each of these terms. From 12 to 8, I am multiplying by 8/12, which is 2/3. But then I multiply by 1/2 for my next set. This is not geometric, so this rule will not work because this is only true for infinite geometric series. From 3/4 to 1/2, I am multiplying, it looks like, by 2/3, and then by 2/3 again. Now that common ratio is 2/3, and since the absolute value of r is less than 1, then this will converge, or it will be defined. This is a geometric series where r is 1/3, so this one is defined. And in D, this is not a geometric series, so this is not defined. So we're going to go ahead and evaluate, if they are defined, what the value of the series is. A is not geometric. B is geometric with an r value of 1/3, so I use the formula shown to evaluate. I get 27/2. and you can check the last two. And that brings us to the end of 8.4. Thanks so much for watching.